Welcome to part 2. Now let's talk about the GPT-3 model architecture. Now it uses the same model architecture as GPT-2, but there are 3 details we'll go into. And this is modified initialization, pre-normalization, and reversible token. Now the first 2 are problems created by the depth of the neural network. To see the problem, let's imagine Chinese whisper played by 96. Assume it's like 96 layers. So the starting string is the cat sat on the mat, and by the time it comes out of the layer 96, it's completely different. Now, each person receives the running version, calculates the change, adds it, and passes the result forward. Because every change is added, they accumulate. Researchers call this running representation the residual stream. Training later sends a correction backward. Now, 2 problems appear here, essentially. 96 large changes can totally destabilize the message. And second, the correction must remain useful across all the 96 layers. Now, the first solution is modified initialization. At the start of training, every layer gets a small editing budget. Think one gentle edit instead of a large rewrite. So, whatever the input string is, you as the person in the Chinese whisper can only make small changes. Now, what this means is GPT-2 starts the weights that produce these changes smaller. The changes still accumulate, but now they're gradual enough to keep the representation stable while the model begins learning. Now, before we get to the second solution, we need to understand layer norm. A representation is a set of numbers. Layer norm recenters and rescales a copy while preserving its relative pattern. So values like 100, 200, 300, like it's a vector, become roughly -1.2, 0, 1.2. The ordering remains same, so no data is lost, but it recenters and rescales a copy to preserve the relative pattern. Now it gives the attention a calculated copy from which to calculate a change. Now pre-normalization describes where layer norm is placed. If you take the current representation, which is essentially make a normalized copy, use that copy to calculate a change, then add the change to the original current representation. The normalized copy does not replace the current representation, and the change itself is not normalized. The sum becomes the current representation for the next layer where the same process repeats. So if we step back, the entire thing is that so that one layer does not completely change the incoming change. So going back to our Chinese whisper analogy, you do not want one layer to completely change the string. And that is what essentially this is doing. And like we will see next, it also makes the learning process easier when backpropagation happens. Now, run it backward. When a correction reaches addition, the same correction reaches both incoming parts. It is not split into shares for this layer and earlier layers. One root crosses the layer work, letting the chain rule calculate how its weights affected the error. The other reaches the previous representation unchanged. And the same pattern repeats at every layer where the weights are tuned. Now, the original transformer put the layer norm after making the change. So every backward correction had to cross layer norm before reaching the previous representation. Now, GPT-2 moved the layer norm onto the processing branch, leaving an addition-only route, so essentially a route where there was no layer norm, through the stack. In layman's terms, essentially this allowed early layers to receive a clearer lesson. This made very deep transformers easier and more reliable to train, helping GPT-3 reach 96 layers. Now we come to reversible tokenization. Pretty much GPT-2's tokenizer. It works the byte level, BPE, because it can always fall back to raw bytes. Every possible string can be encoded and then decoded back exactly the original text with no unknown token loss. So essentially nothing new, all inherited from GPT. There is though one architectural change, and it is worth stopping on. Now, GPT-3 uses alternating dense and locally banded sparse attention patterns, similar to sparse transformer. Now we'll unpack that. And so we need to understand the difference between dense and sparse attention. Standard attention, let's call it dense, lets every token look at the very earlier token. In a sequence of length n, that is n by n comparisons, position 100 attends to all the 99 before it. Positions 2000 attends to all 1999 before it. As you can see, it's really powerful, but the cost grows with the square of the sequence length. double the context, and the attention gets 4 times as expensive in both compute and memory. The 2048 token context across 96 layers, that quadratic term is like really huge. Now, sparse attention is the fix. Instead of letting every token see every other token, you restrict each token to a limited, fixed pattern of positions. Locally banded is the simplest version. A token attends mostly to its recent neighbors, a band around it, plus a few longer range links. So information can still travel across the whole sequence in a couple of hops. You see how this is the banded sparse is doing the recent neighbors for few long range hops. So each token now looks at roughly the square root of n positions instead of all n, which turns that n squared cost into something much closer to n times root n, far cheaper. And for most tokens, the nearby context is what matters anyway. But then GPT-3 doesn't pick one, it alternates. Some layers run full dense attention, so the model keeps layers with a true global reach. Other layer runs the cheap banded sparse pattern. Interleaving the two is a deliberate trade. So that way, we buy back most of the compute and memory. A fully dense 96 layer 2048 cortex model would cost, while keeping enough dense layers that nothing important is lost. And that is the only architectural change from GPT-2. Everything else is identical. Scale more. So this is where the sparse transformers paper was introduced. The problem that they tackled was exactly what we spoke about. Full attentions n squared cost makes very long sequences infeasible. Their fix was to factor attention into few fixed sparse patterns, while stacking those patterns still lets any position reach any other in a small number of steps. That drops attention from order n squared to order n root n, plus some memory saving tricks that let them train deeper. GPT-3 borrows that sparse idea for a subset of its layers. Now let's talk about the scale ladder itself. Now we have been talking about the scaling. Now this shows the scale ladder. GPT-3 small is 125 million, and from there it keeps going, and then GPT-3 is itself is 175 billion params. 96 layers, 1228 size, so on. Now let's try and define every symbol. N params is the total trainable parameters, the countable knobs that the model can tune. 175 billion means 175 billion numbers. In layers is the number of transformer blocks stacked. Deeper means more sequential reasoning steps. In this case, it's 96. The model is a number of units in each bottleneck layer. Essentially, if you could think as like the width of the hallway. The feed-forward layer is essentially 4 times this. And heads is the number of attention heads per layer. Essentially, the parallel attention views. The head is the dimension of each head. Batch size is measured in tokens, and the learning rate essentially decreases with size. Larger models need a smaller learning rate, but can use a larger batch. Context window is 2048 tokens, as we had already defined in the few-shot definition, which is about 500 words. The models are partitioned across GPUs along depth and width to minimize data transfer. Now, if you remember paper 3, the precise architectural parameters for each model, the exact split of layers versus width versus heads, were essentially chosen for computational efficiency and load balancing across GPUs. And if you remember our last paper, loss is primarily set by scale, which is parameter, data, and compute, not whether we spend those parameters on more depth or more width. So essentially, if we start seeing new capabilities in GPT-3, we can attribute it to scale, not to the architecture. Now let's go a little deeper into the scale ladder. Picture one layer's weight model as d model by d model grid of numbers. Double the side of a square, and you get 4 times the cell. Now the question is, if you double d model, does compute per token double? No, it roughly quadruples, because attention and feed forward scale with d model squared plus n layers, which is why total compute is about, if you remember, C is 6n tokens from paper 3. Same formula, just now that n is now huge. Now the dataset is where the real engineering hides, and it comes down to the problem and the fix. The raw material here is common crawl, nearly 1 trillion words stripped from the open web. It is enough to train even the biggest model without ever repeating data. But raw web text is noisy and low quality. SEO spam, keyword stops pages, navigation menus, the key patterns, and whatnot. And a lot of it is barely language at all. Wikipedia and the two book collections are the opposite, much smaller, but clean, well-edited, information-dense text. Now, what the team does with the mix? If they weighted each source purely by its size, Common Crawl would drown everything else out. Most of the data would be noisy pile, and the good stuff would be a rounding error. Instead, they intentionally break that proportionality. They hold Common Crawl down to a fraction of a single pass, 0.44 epochs. Essentially, which means the model sees less than all of it. While the small high-quality sets get sampled over and over, Wikipedia about 3.5 times, web text to nearly 3 times, books once or twice. Same 300 billion training tokens, but deliberately tilted toward the clean sources. Why do they do that? Essentially because of a finding that runs all through the language modeling. Not all tokens are equal. A small amount of high-quality data is often worth more per token than a huge amount of low-quality data. So the goal is to be best of both worlds. Common Crawl's broad coverage of the whole internet, plus repeated exposure to the dense, reliable signal in books and in Wikipedia. Now, there's no formula. The team made a judgment call over how much each source should contribute. Now, coming to this important sentence, this is a pretty big strategy. GPT-3's team made a deliberate choice, built a much larger model, but trained on relatively fewer tokens than was normal at the time. The example makes it clear. GPT-3, 3 billion, is almost 10 times larger than Robert A. Large, at 355 million parameters. Yet, both used roughly the same 50 petaflops per days of compute. Same budget, very different split of it. Scaling laws found that given a fixed compute budget, you reach lower loss by pouring most of the budget into model size, a much bigger model, and training it on comparatively less data, stopping it before fully convergent. And what the paper said was bigger models are simply more sample efficient per token. So GPT-3 is large on purpose, following the compute optimal recipe we derived last episode. Now, after this paper, when Chinchilla came out, the new paper, a lot of things changed, but that was why they did what they did with that knowledge available to them during the publication of this paper. Now, here's the key outcome of this paper. Larger models use in-context examples more efficiently. Now, here, there's a simple way to picture it. Think of teaching kids to remove random symbols from hello. Okay. You put in some random symbols, H, exclamation mark, hash, whatever, and make hello. A small kid needs many examples and still struggles. A bigger kid catches the pattern after 2 examples and kind of skyrockets from there. An even bigger kid understands even from the instruction and just when you say remove symbols. And that's pretty much it. Now, to define the axis K in the x-axis is essentially the number of demonstrations in the prompt. You can see as the scale becomes bigger, the number of examples needed to reach the same loss is lower. Now let's look at the results. We're not going to walk through everything because there's like many, but let's talk about the first one. This one is a long-range memory text. You give the model a whole paragraph and ask it to predict the very last word. But the passages are handpicked so that the final word is guessable only if you have read the entire paragraph, not just the last sentence. Someone who just reads the last line cannot get it. Someone who reads the whole passage can. So this one directly measures whether the model is holding the broader context in mind, not just the local phrase. Now you can see GPT-3 makes a big jump here compared to Soda. Now you can see how the accuracy climbs across from 0 shot, 1 shot to few shots. Now you can see trivia QA questions essentially looks like ordinary trivia you find all over the web. That format is in distribution, so GPT-3 answers it pretty well, even cold. Now, web questions have a peculiar house tag. Its questions and the expected shape of their answers are kind of unusual. So with 0 examples, GPT-3 doesn't do that well, or how to format the answer. It has knowledge, but it is thrown by the format. And that is why the paper suggests that questions and answer style may be out of distribution. The larger 0 to few gain perhaps suggests that GPT-3 appears to be able to adapt to this distribution, recovering strong few-shot performance. Now let's jump into common sense reasoning. 3 data sets that test physical or scientific reasoning, as opposed to the pure knowledge recall we just saw. This is the group where GPT-3 results are mixed, so let's walk through it. First, physical QA. Common sense questions about how the physical world works. GPT-3 gets 81% 0 shot, and then 82.8% few shot, which actually edges past the prior fine-tuned Soda, a real win, though still about 10 points below humans. And the paper flags Pika for possible data, so kind of marks the number with an asterisk. Second, ARC, the multiple choice science questions from grade school exams, split into an easy and harder challenge. GPT-3's few shot climbs well above its own zero shot on both splits, but it does not reach fine-tuned specialist, which sits at 92 on the easy and 78.5 on challenge, furtively ahead. So overall, in-context learning shows mixed results on common sense reason. A clear winner Pika, but only middling on ARC and Open Book QA, with small and inconsistent gains from adding examples. Now let's cover arithmetic. Now you've probably heard that language models are bad at math. Now, it is a bit true, but it depends on which arithmetic. If you look at the table, you can see that on small problems, it is genuinely strong. Two-digit addition is basically solved at 100%. Two-digit subtraction, 98%. Three-digit, 80%. But push the size up and it falls off a cliff. Four-digit addition drops to about 25%. So it is good at small and subtract and bad at large numbers and at multiplication. Math is good for the easy end. Math is bad. It's good for the hard end. Now, the part that makes the good end impressive is that this is not memorization. The author searched the training set for the exact test problems and found only 0.8% of the three-digit additions and 0.1% of the subtractions actually appeared there. Nowhere near enough to explain the scores. So the model is not looking the answers up. And when GPT-3 gets a problem wrong, it makes human-style slips, like forgetting to carry, which is what something actually stepping through the addition gets wrong. Not what a lookup table would do. Now let's be precise about what does this mean, because it's easy to overread. This is not GPT-3 being a calculator. A calculator has an exact algorithm. Give it any numbers, any size, and it is always right. And bigger numbers are no higher. GPT-3 is the opposite. It is reliable on two-digit sums, shaky by four-digit, mostly lost on five. Now, there is no general exact arithmetic engine inside it, so we do not call it a calculator. What the evidence does support is far more subtle and more interesting. The model has picked up a real but approximate procedure for adding small numbers. Three things point that way, and they are why we read this as emergent reasoning rather than a lucky trick. One, it generalizes to specific problems that were not in its training data. So it learned the operation, not the instances. Two, it mistakes our procedural, a drop carry, not a random number, which is the signature of a mechanism actually running the steps rather than retrieving the answers. And three, the ability appears only at the largest scale, out of nothing, but next token prediction, with no arithmetic anywhere in the training objective. Learned, generalizing, and procedure-like, and essentially switched on by scale. That is what emergent reasoning means, and it is much more careful claim than GPT-3 cannot do math. And the scale point is the most important one, because this ability appears only at the very top of the size ladder. Plots all 10 arithmetic tasks across the model side, and it is nearly flat. Small and mid-size model scores close to zero on everything, until a sharp jump at the largest model. In fact, the full GPT-3's zero-shot arithmetic significantly outperforms every smaller model's few shot. The capability does not fade in gradually. It switches on near this 175 billion parameters. That is emergence, a skill that is absent at every small scale and then appears. Arithmetic is algorithmic, not language recall. Its emergence hints at real procedural capability coming out of pure next token prediction, but only on the small cases and only at full scale. So let's come to contamination. Contamination is test data leaking into the trains. It's an old worry. We spoke about it a lot in the GPT-2 paper. It already ran its own post-hoc overlap analysis and found the effect relatively encouraging, meaning it's small. So why does GPT-3 talk about it so much more in this paper? Well, because scale cuts both ways. The same problem GPT-2 could wave off becomes serious enough at GPT-3 scale to demand a systematic study. What they did was they constructed clean versions of benchmarks by the n-gram overlap search. The x-axis is lower bound on how much is known clean with high confidence. The y-axis is the difference in performance when evaluating only on the clean set. If the delta is near zero, that means essentially it's not inflating the scores. Now, rather than read every row, the per benchmark picture comes down to one question: how much got flagged versus how much it actually mattered? Now, the headline of the table is a bit counterintuitive. So let me say clearly, a huge amount got flagged, but very little of it actually inflates the score. For example, for reading comprehension, it flagged 90% potentially contaminated because the source text was present in training. but the question and answer pairs were not. The model gains only background info, it cannot memorize the answer. Now, this is the key line. Performance on most benchmarks changed negligibly. And here's the worry in plain terms. Think of checking whether a student cheated by comparing their score on questions they had seen before against questions they definitely had not. If the two scores match, cheating did not help. But what if the not seen questions happen to be the easy ones? Then their clean score is high for an unrelated reason. And the two scores match not because there was no cheating, but because the two biases quietly cancel. The cheating boost on one side and easier clean set on the other. And the paper admits it, that it cannot fully rule out that story. So how can they still say contamination is not a big problem? Well, two reasons. First, the lucky cancellation would have to happen independently across dozens of benchmarks. One coincidence is believable, 40 is not. Second, they run a control. Small models which do not have capacity to memorize much show the same clean versus full pattern as GPT-3. If memorization were a driving pattern, it would disappear for models that cannot memorize it. It does not. Now, it's true we cannot prove zero effect, but the scores do not drop on clean data, and the two independent checks argue against the coincidence explanation. As models train on web scale data, test set overlap becomes inevitable. And the only defense is what this section does: systematic measurement, plain reporting, and outright removal. Now, what are GPT-3's limitations? Well, the paper lists those here. Even at 175 billion parameters, GPT-3's text generation still slips. Over a long passage, it can repeat itself, lose the thread, contradict what it said earlier, and it has blind spots. The paper singles out common sense physics as one of the blind spots. For example, you ask GPT-3, if I put cheese into the fridge, will it melt? And it struggles. The kind of physical intuitions any child has. Second, this connects directly to those comparison failures. A structural limitation. GPT-3 is autoregressive. It only ever reads left to right. So they chose that on purpose because it makes sampling and scoring likelihoods easy, which is what in-context learning needs. But it means no bidirectionality. And the tasks that benefit most from bidirectionality are precisely fill in the blank. Comparing two pieces of text and carefully reading a long passage, which is likely why those comparison tasks came out weak. It's not a bug, it's mostly an architectural trade-off. Third, and the deepest one, a limitation of the training objective itself. Next token prediction treats every word as equally important to get right. The model has no sense that some tokens carry the meaning and others are failure. More fundamentally, self-supervised prediction forces every task to be squeezed to predict the next token. When what we actually want from a virtual assistant is more goal-directed action, doing something in the world, not just predict text. Fourth is grounding. The model has never seen a video or touched anything, so it lacks a huge amount of context about how the world works. It is also strikingly sample inefficient. It is cheap at test time, 1 or 0 examples, but during pre-training, it reads far more text than a human sees in a lifetime. So it does not learn anything like the way we. The paper's conclusion is candid. Scaling pure self-supervised prediction will hit a ceiling, and getting past it will need a different approach, learning the objective from humans, fine-tuning with reinforcement learning, or adding modalities like images. These are some of the things we are going to study in the next paper. And last, the open uncertainty at the very heart of the paper. They admit that they do not fully know whether FewShot is genuinely learning a new task at inference time or just recognizing a task it is already absorbed during pre-training and adjusting to the format. It is a spectrum. Where GPT-3 sits on the spectrum differs task to task, and they say plainly that they cannot cleanly separate the two. All of these limitations, all of these 5 limitations, shows that these are gaps that instruction tuning and human feedback can fill. Now, the next section is misuse. We just look at one case and then close off this analysis. Let's look at the gender section. This covers fairness. Internet-trained models have internet skill biases. For gender bias, 188 occupations were tested with the prompt. The occupation was followed by a male versus female identifiers. 83% of occupations were more likely followed by a male identifier, and the association was higher for historically male-leaning occupations. They also probe race and religious bias with similar patterns. The model is a mirror. If the training data says detective more often gets followed by a he than she, the model learns that. The probability of a man versus woman after an occupation context is a measurable bias metric. Now, this brings to the end of the paper. Now, we are at the FAQ section. These are some of the questions I had when I was reading the paper, so I made them into an FAQ. what aged badly, considering this is a 2020 paper? The result did not age badly. The recipe, though, it changed. GPT-3 proved that scale worked, but the later paper, Chinchilla, showed that this was indeed underfed on data file size. After that, the field stopped treating parameter count as the whole story and started treating scale as a balance between model size, token count, and data quality, and inference cost. 2. How did we solve GPT-3's problems? Well, it was not one thing. It was a combination of multiple things like cleaner data, better compute balance, retrieval in tools, longer context. And then, of course, the assistantship problems were solved by post-training. Demonstrations taught the model what a good answers look like. Preference data taught it which answer would people prefer. RLHF and safety training pushed it towards helpful and being honest and harmless behavior. All of that we'll talk about in paper 5. 3. Is scale dead? Well, scale still matters, but scale now means more than parameter count. It means better pre-training, better tokens, longer context, inference time compute, so on and so forth. We are no longer saying that the parameter count is the only thing that is important. 4. Are we running out of internet data? Well, now in 2026, high quality public human text is becoming a real constraint and may get tighter on 2028. But the labs are not staring at an empty internet. They filter harder, they use code and book, they license data, they train on images and audio and video, they generate synthetic data, and they repeat strong data carefully. The bottleneck is quality and the rights and mix, not like a single source. 5. Is GPT-3 the same as ChatGPT? No, GPT-3 is in this paper is a frozen base model. It predicts next tokens. It has no instruction tuning, no RLHF, no assistant contract, and no product safety layer. ChatGPT is a descendant after post-training and deployment work. GPT-3 is the engine. GPT is the engine taught to answer like a helpful assistant. We finally come to the end. Paper 1 gave us the architecture, the transformer. Paper 2 gave us the pre-training thesis, the next token prediction on web text, and where zero-shot task behavior starts. Paper 3 gave us the engineering economics for it, laws of the power law, and how we can train a huge model on few tokens and stop early. Paper 4 gives us measurement, essentially same architecture as paper 3, but what happens when you scale, what new capabilities emerge, and what are the sort of risks that we see, and that we start seeing few short learners in some narrow slices at this scale. And finally, paper 5, which is going to be the next one, teaches this few short learner how to be helpful, safe, and aligned. Thank you for joining me on this episode. Let me know how you find this series, and if you have recommendations around other papers that I should read, do drop it in the comments. Do not forget to like, share, and subscribe.